In the last lesson, we went through all the formulas, so in this lesson, we're going to work these last few problems and then be done with the notes. So in exercise 4, we have the oxidation of water to produce hydrogen peroxide, and we're given the delta G values, and so it just wants us to find delta G for the reaction or for the formation. So it's going to be quite straightforward. We're going to use the delta G reaction is going to be equal to the summation of delta G products minus the summation of delta G reactants. So just like we did for enthalpy. And so we'll start with our products. We've got the H2O2, so delta G. The reaction is going to be equal to 2 times negative 27.2. Put the decimal in there. And of course this is kilocalories this time. It's a little bit different. Still works the same. And then minus the reactants. We have 2 for water, and it is liquid water, and that's the only one they're giving us. But if you're looking at a table, make sure you're looking up liquid water and not gaseous water, because they are 2 different values. 56.7 kilocalories per mole. And then, of course, oxygen is 0, because just like delta H, delta G for the elements is 0. So when we get done with that, our answer should be 59 kilocalories per mole. So that one is pretty straightforward, because it's just like delta H. So let's move on. Give you a second to finish writing that. I know I sometimes write too fast. I apologize. Alright, so the next exercise is carbon and diamond, and I can tell you right now on your notes the answer key is wrong, and you'll see that when we work it. So this is just like what we did when we did Hess's law, where we can rotate things and make them add up to our final equation. So we're looking for diamond going to graphite. So this one we're going to leave the same. We don't need to change it. But this one we're going to need to reverse. And just like delta H, when we reverse it, we change the sign, or if we use an integer, we multiply the delta G by the integer. So we're going to keep the carbon, and we're just going to do DIA, we're going to abbreviate that, plus O2 is going to CO2, and we're going to reverse this one. So we're going to say CO2, and then we got carbon graphite, and plus O2. And of course this one stayed the, oops, out of habit, almost did delta H, is negative 397 kilojoules per mole. This is an old note, so it needs to be per mole. And then because we reverse this, we're going to reverse that sign. So delta G is going to be 394 kilojoules per mole. We cancel our carbon dioxide, cancel our oxygen, so we have carbon diamond going to carbon, that looks like CD, let me just do that, carbon graphite, and then our delta G will be a negative 3 kilojoules per mole. Your notes say positive, but clearly whenever we say that that was positive when we reversed it, then it's a negative 3, which means that it is thermodynamically favored, or what we used to say as spontaneous. But kinetically, it happens so slow that it's pretty much doesn't happen. So that's the difference between kinetics and thermodynamics. Thermodynamics says, yes, it could happen, it's spontaneous or thermodynamically favorable, but kinetics says, hold your phone, so slow it's essentially not happening. So now for exercise 7, this time we're given delta H and delta S values, and it wants us to solve for the equilibrium constant, and so we're going to look at that, and this one's going to be a long problem. We're going to have to solve for delta H because we don't have that, so we're going to solve delta H and delta S using the summation, with summation. Then we're going to solve for delta G using the delta H minus T delta S. Then the last step would be the delta G Ratlink equation. Oops, negative Ratlink equation. So it's going to be a process. So I'm going to put a new screen up, and because there's no way I can fit that on there. So we'll work that real quick. So let's start with delta G first. Let's erase that. I mean, not delta G, you can't do that first. Delta H. So we have delta H is going to be equal to we have 2 moles times negative 826. And for space, well, let's go ahead. I harp on you all the time, use your units, kilojoules per mole. Okay, and that's going to be minus the nothing. Going to be minus 0 because those are both elements. So then our answer for that is negative 1652 kilojoules per mole. So now let's do delta S. Delta S is 2 times 90 joules per K mole, or mole K, however you want to do that, minus, now for entropies, it doesn't matter that they're elements, they still have values. Remember, entropy is the oddball out. Plus 3 times 205. Habit, I wrote kilojoules. And then that ends up being a negative 543 joules per mole K, sorry. I know that when I use my delta G equation, I'm going to need this to be in kilojoules, so I'm going to immediately convert, and so it would be a negative 0.543 kilojoules per mole K. That way when I go to plug it in the delta G equation, I'm good to go. It's a good habit to get into, and so you don't accidentally use 1 in joules and 1 in kilojoules. So now let's do delta G. It's equal to delta H minus T delta S. So let's plug that in. We've got negative 1652 kilojoules per mole minus, our temperature was 25 degrees Celsius, so 298 K. We have to be in Kelvin because of this Kelvin right there, times negative 0.543 kilojoules per mole. So I get my delta G value is a negative 1490.2 kilojoules per mole. So now the last step is I'm going to use delta G is equal to negative Ratlink and solve for the equilibrium. So the R value, remember, is 8.3145 joules per mole K. So that means I cannot keep this in kilojoules. I'm going to need to put it in joules. And there, in 1 kilojoules is equal to 1,000 joules. So this number is going to become, ends up being, when you put it in scientific notation, 1.49 times 10 to the 6 joules equals negative 8.314 joules mole K, times our temperature was 298 times the natural log of K. So when you do all that math, you get that it's equal to, the natural log of K is equal to 601. And then when we want to get rid of the natural log, we just take e to the 601, and when you type that into the calculator, you probably don't see this very often, but it says overflow, which means it's too big of a number for our calculator. So on your notes, you'll notice that K is equal to 10 to the 261, which is a really big exponent. So this would definitely have products favored on this one. Now, on the AP exam, they're not going to give you one that's going to be an overflow. That's just too big of a number, and they're not going to do that. But so you would not be able to get this number. It's just what someone, I guess, who has a more high-powered calculator are able to do. I think you actually have to take it out of the natural log and put it into log, but they're not going to ask you to do that. But you see the process. The next one won't be that way. It'll actually get a number. Okay? All right, let's go to the next problem. All right, this one wants us to calculate the thermodynamic boiling point of water, liquid water to gaseous water. Okay, and a couple of things we need to recall is that during a phase change, the system is at equilibrium, so delta G is 0. So we're still going to use this delta G is equal to delta H minus T delta S, and then we're set that equal to 0, delta H minus T delta S. And the notes tell you how it's derived, but we'll go ahead and do it. We're going to subtract delta H from both sides, just like simple algebra. So then we have negative delta H is equal to negative T delta S. So if I decide to divide both sides by negative delta S, then T can say, therefore, T is equal to delta H over delta S because our negative signs cancel out. So now we just plug and chug. This is in joules, this is in kilojoules. So we got to flip them around. To me, it's easier to make this one be kilojoules because it's a divide by 1,000. So because just like before, there's 1,000 joules and kilojoules. So this can be 0.1188 kilojoules per mole. Okay. So now we can plug that in. We've got 44 kilojoules per mole divided by 0.1188 kilojoules per mole, K. So these units cancel, and when we do all that math, we get that our temperature is 370 Kelvin. Okay. Now, just for grins to kind of ballpark it and see if we're on the right track, if I take 370 minus 273 to put it back in Celsius, I would get approximately 97 degrees Celsius, which is close to our 100. It's not unthinkable, but if we did this and we got like 50, then we probably did something wrong because we know that the boiling point of water is not 50, but 97 with these values, we're pretty close. Okay. We just did that one, so let's go on to the next one. For this reaction, oops, oh, I hit too much. There we go. For this reaction, calculate the equilibrium constant. So here we have at 25 degrees Celsius. They already gave us our delta G, so we don't have to do all that jazz that we did a while ago when we had to calculate delta H and delta S and delta G. So they make this easier. So we're going to use delta G is equal to negative Ratlink. Okay. Recall that R again is 8.31. We got 45 joules per mole K. So we got to get this delta G into joules because it will not work that way. So there are 1,000 joules in 1 kilojoule. So this becomes negative 257,200 joules. So let's plug it in. Negative 250,200 joules per mole is equal to negative 8.3145 joules per mole. K times 298K is the negative log of K. I ran out of room. I write too big. So the natural log should be equal to 103.8. And then in order to get it out of the natural log, we're going to say e to the 103.8. Luckily, this one does not give us an overflow. And we get an answer of 1.20 times 10 to the 45th, which favors products for sure. That's big. Not as big as the other one, but it is much larger than 1, so it favors products. Okay? All right. That is, I think, the last problem we need to work. So let's just go through, I'm going to go very quickly through the end because you guys are proficient readers. You don't need me to read to you. But here's a good summary that you should make sure you know for the test. If delta G is negative, then it's thermodynamically favored. It says E cell would be positive. We haven't got there. And so I'm going to try to make sure none of that shows up on the thermodynamics test. It will on the last unit. If it's 0, we're at equilibrium, and if it's positive, it is not thermodynamically favored. Of course, this would be our old style of spontaneous and not spontaneous. Okay, that helps you think that way. This is a super good table, or super good thing to understand. And when you're looking at this, keep in mind that when you have this equation, it makes sense. Whoops. Delta H minus T delta S. Okay. So if this is negative and positive, then it's going to be favorable at all temperatures. Because remember, if this is positive, you're going to always be subtracting. So you're subtracting from a negative, it's just going to make it more negative for delta G. So it would be favorable at any temperature. Okay. But if you have a positive and a positive, it's only going to be thermodynamically favored at high temperatures. And that's because you've got, a positive, and then when you minus when you're minusing from that, it would have to be a high enough temperature that this structure or this component of it would take effect. And then if you have a negative negative, it would only be at low temperatures. Okay, and that's because this side would be negative, and then when you minus a minus, of course you get a positive. So it would only be at low temperatures so that the positive doesn't overtake the negative. And then if you're positive negative, it will never ever be thermodynamically favorable, because in this case you'd be taking a positive, and then when you minus a minus, it's positive, you'd be adding two positive numbers, so you would never get it to be favorable. If for some reason you get to the test, either in class or on AP test day, and you can't remember this little table, throw in some dummy numbers. Okay, throw in some negatives and positives and just kind of play with it. And see what you think. I mean, you know your rules. A negative minus a negative is a positive. So if you're adding a positive to a negative, that kind of thing. So you guys got to look at your temperatures. Okay. The rest of this is relationship between delta G, K, and E. That will be important when you get to the AP exam, because those things all go together. But for our unit test, like I said, I'm not going to show up any E cell because we haven't learned what it is yet. And here's some common misconceptions that I'm going to let you read through because you are all good readers. Okay? Anyway, that is the end of our video lesson, and I will see you after spring break. Make sure you do all your worksheets.